7-6, exponential functions. So our objective for this section is to evaluate and graph exponential functions. Our essential understanding is that some functions model an initial amount that is repeatedly multiplied by the same positive numbers. In the rules for these functions, the independent variable is an exponent. Okay, so the definition of an exponential function is pretty much going to be a function where you have a variable that is in the exponent. Okay, so an exponential function is a function of the form y is equal to a times bx, where a can't be 0 and b is greater than 0. Okay, the reason why a can't be 0 is that if you multiply anything by 0, the answer is going to be 0. So this would just be y is equal to 0 no matter what numbers you plugged in for x. Okay. Also, b has to be bigger than 0 because if b was, say, a negative number, weird stuff happens that we'll see a little bit more in the next chapter. Okay. So whereas you could do various positive exponents, as soon as you do something like that, that gives you something that is not real anymore. Okay, so the base has to be positive, called the base. Okay, the base has to be positive, and when it is, we get functions that look like this. Here, right, only the 2 is raised to the x power, not the negative sign. So really, for the blue one down there, we're looking at something like this. Okay, so still, or even better, kind of like that. Okay, still 2 is raised to the x power and the base is not negative, even though it looks like it is. Okay, so here we have an exponential function, y is equal to 2x. Here, y is equal to negative 2x. Here, y is equal to 1/2. And here, y is equal to negative 1/2. So you can see there's really 4 different types here. We have the red one on the left that's going up, the blue one over here on the left that's going down, this one's going down, this one's going up. So we have a couple different types of situations that we can have happen. Okay, so suppose all the x values in the table have a common difference. If all the y values have a common difference, the table represents a linear function. If all the y values have a common ratio, then the table represents an exponential function. So this is when we have just raw data, like in this problem. Okay, does the table or rule represent a linear or exponential function? So if we have just raw data and we notice that the x values all go up by the same amount, in this case they're all +1, then we can figure out, is this a linear function or an exponential function? And we see that to go from one to the next, right, the difference between here is going to be 2, the difference between here, well, so they're not going to be the same. So we're not going to be adding something to get to the next number each time. But if I multiply the previous number by 3, I would get the next number. Okay, so that means there's a common ratio. So the ratio is 3, right? To get to the next one is 3, which means this is an exponential function. Okay? For part B is a little simpler because this rule is a linear function. How can I tell? The variable is not in the exponent. It would be an exponential function if it looked like this, if the variable was in the exponent. And I can show that with data as well. If I make a table just like the one above, if I have 0, 1, 2, 3, if I plug in 0, I would get 0. If I plug in 1, I would get 3. 2 would be 6. 3 would be 9. And you can see that each one of these has a common difference, right? You would be adding 3 to get to the next one. Okay? Let's try a got a problem. Okay, so I can just look at my first set of data right here. the x values are all plus 1, and the y values are all plus 2. So this is a linear function. Okay? This one is exponential. How can I tell? Because the variable is in the exponent. So whether we have data, raw data, or whether we have an equation, we can tell whether or not we have an exponential function. Okay? Let's use an exponential function. So suppose 30 flower beetles are left undisturbed in a warehouse bin. The beetle population doubles each week. The function f of x is equal to 30 times 2 to the x power gives the population after x weeks. How many beetles will there be after 56 days? Well, first thing, right, we have our function 30 times 2 to the x power, where x is weeks, and I want to input days. So before I can do that, I have to change it to weeks. So since there's 7 days in 1 week, hopefully we all know that, we take 56 divided by 7 to give me 8 weeks. Okay, so we're going to input 8 into my function to give me 30 times 2 to the 8th power. Now remember order of operations. We do not multiply the 30 and the 2 first. We raise 2 to the 8th power first. So this becomes 30 times 256, which becomes 7,680. Okay? So just make sure the trick right there is to either do that by hand, 2 times 2 times 2 times 2, 8 power, 8 times, or maybe your calculator has a button that looks like this. Maybe your calculator, let's use X. Maybe your calculator that has a button that looks like that. Either way, whatever way your calculator is set up to raise something to some power, just make sure you know a little bit about how it works. Okay? Let's try a guided problem. Initial population of rabbits triples every half a year. The function 20 times 3 to the x power gives the population after x half-year periods. How many rabbits will there be after 3 full years, which means 6 half years? Okay, weird conversion there, but hopefully that makes sense. So we're going to find f of 6 with 20 times 3 to the 6th power. So that's 20 times 3 to the 6th. It's going to be 729 times 20 gives me an answer of 14,580 rabbits. Okay. Let's graph an exponential function. Okay. So to graph a function where we don't know what it's going to look like beforehand, best way to do this is to make a table. Okay. So let's make a table. Let's get some x's and let's get some output y's. Let's start with some negative numbers. So for -2, we're going to have 3 times 2 to the -2 power. 3 times 2 to the -2 power. Well, remember negative exponents mean fractions. So that's 3 times 1 over 2 squared. So 3 times 1 over 4 is 3 over 4. And let's just put this in a decimal so that way we can write this a little bit better. So it's going to be 3 over 4, which is going to be 0.75. That way we can graph this a little bit better. Okay. What about this one? Let's plug in -1. So 3 times 2 to the -1 power is going to be 3 times 1 over 2, which is going to be 3 over 2, which is 1.5. Plug in 0. 3 times 2 to the 0 power. Anything to the 0 power is 1, so that's just 3. 3, let's plug 1. Let's go 2. Let's plug 3 in. And maybe 4. Let's get a good time. Let's get a good pattern here. Maybe you see the common difference already. Maybe you see how you're getting from one term to the next term. Well, let's see. 3 times 2 to the first is 6. How do you get from 3 to 6? Add 3. Or, since this is an exponential function, and we know we have to have a common ratio, multiplying by 2. Let's see if that holds up. 3 times 2 squared is going to be 3 times 4, which does hold up to 12, which makes the next one 2 times more than that, and then the next one 2 times more than that. Let's graph this. So negative 2, back 2, up 0.75. It's pretty close. Negative 1, 1.5. 0, 3. 1, 6. 2, 12. 3, 20. 3, 23, 24. So it's right off the top of the graph right up there. Hopefully you get the idea of what this pattern looks like is if it doubles every time going to the right, when I go to the left, it's sort of going to get cut in half, in half, in half, in half, in half. But since I'm not subtracting anything, it's never going to go below 0 because this is 3 times some fraction. 3 times a fraction is never going to be negative. Okay, remember the biggest negative exponent we can put in here is anything we want. And if we put something really big, something like that, that's going to be 3 times 1 over 2 to the 20th. 2 to the 20th happens to be about 1,000,000. So it's 3 over 1,000,000. That's still not negative. Okay, so no matter what, this graph is never going to cross the x-axis. So we're going to get something that looks kind of like that. Okay, and you can see we have the function going up as we go left to right. Starts off going very slowly up, then it gets faster and faster and faster until it gets very fast. That's sort of the behavior of an exponential function. Slow growth at the beginning, very fast at the end. Let's try a got it problem. What's the graph of 0.5 times 3 to the x power? Okay, so let's make another table. A little crooked. A little table. Okay, so let's plug in negative 2, negative 1, 0, 1, 2, and 3. Okay. When I plug in negative 2, 0.5 times 3 to the negative 2 power gives me 0.06. 0.5 times 3 to the negative 1 power would be 1/6, which is 0.1, or it's not 0.1, 0.17. 0 would be 0.5. 1 would be 1.5. Right? 3 to the first power is 3 times a half is 1.5. 2 would be 4.5. 3 would be 13.5. And if you did notice that even though these are weird decimals, each time we're going up by a factor of 3. The base of the exponential expression. Let's graph it. So, negative 2. Negative 2, negative 0.6, 0.06, 0.17. Kind of hard to get these exactly right, but we'll do our best. 1.5, 4.5, 13.5 off the graph, so that's way up here. So we're going to get a graph that kind of looks something like this. Nice exponential function. Okay, Let's try one that looks slightly different with another guided problem. Okay? So now my table is almost the same, except it's going to be negative 0.5. So when I make my table again, instead of multiplying by a positive number, okay, now we're going to be multiplying by a negative number. So this input doesn't change, and so instead of 0.06, I have negative 0.06, negative 0.17, negative 1.5. Sorry, negative 0.5. All right. 1 is negative 1.5, negative 4.5, and negative 13.5. So this graph is going to look pretty much the same thing, except instead of being kind of like this, it's going to go exactly the opposite way. Let's make a nicer one than that. Okay, so we have 0.06, 0.17, and let's make this a little closer. 0.06, 0.17, 0.5, 1.5, 4.5, and here's where my fingers hit, and we get a nice graph that looks like that. Okay, so you can see that this one is going down while the other one was going up. Okay. Graphing an exponential model. So computer mapping software allows you to zoom in on an area to view it in more detail. The function 100 times 0.25 to the x models the percent of the original area the map shows after zooming in x times. In Miami, see, we're way out. 1 time, 2 times. Graph the function. Okay, so again, when we're not sure what the function is going to look like ahead of time, we are going to make a table. So my equation is 100 times 0.25 to the x power. All right, so let's plug in some numbers. So we're going to make our table, x, y. Let's plug in 0. Do we have to plug in negative? No, because x is how many times we zoom in. So we can zoom in 0, and this is going to be 100. We can zoom in once, and it's going to be 25. We can zoom in twice, and then the answer is going to be 6.25. 3 times, 1.56. 4 times, 0.39. That should be enough to graph this. So 0, so we can see each line goes by 10. So 0, 100 would be there. 1, 25, right there. 3, 6.5. Already, we're getting pretty small. 1.56. And before we know it, we have a flat graph. So we have our graph that looks kind of like that. Okay. So all we have to do here is plug in the numbers in order to get an idea of what the function looks like. Got a problem? You can also zoom out to view a larger area on the map. The function 100 times 4x models the percent of original area of the map shows after zooming out x times. Graph the function. So same idea here is now we're just going to go x, y, plug in 0, still get 100. Plug in 1, we get 400. Plug in 2, we get 1600. Plug in 3, and we get, oh, that's going to be a big number. 4 to the third is 64. So that's going to be 6400. Okay, so if we have our graph, it's going to start, at 0, 100. 1 is going to go up. Well, let's make this a little bit better. 1 is going to go up, 400. 2 is going to go up to 1600. 3 is going to go, oh, it's going to go way up. So we're going to get a graph that kind of goes up very quickly, as opposed to the graph over on the top that went down very quickly. Okay? And we can notice a few things. Notice that the base there is a decimal lower than 1. And notice that the base here is a number greater than 1. We'll dive into that a little bit more next section. Part B, what is the percent change in the area each time you zoom out in part A? Well, if you remember, percent change is y2 minus y1 over y1. So my answers were 25 minus 100 over 100. So that is a negative 0.75. So that's a negative 75%. So we're changing by, the percent change is 75% decrease, or zoom in, or 75% increase, however you want to think of it. But each time I zoom in another time, we're changing by 75%, right? From 100 down to 25. Okay. In the concept bite after lesson 6.1, you solved a one variable linear equation using graphs and a graphing calculator. In the next example, you will write each side of an equation as a function and graph the functions. The x value where the functions intersect is a solution. So here's our function. Unfortunately, we cannot just solve this using algebraic techniques. We can later, when you learn about how to solve exponential equations, but for now, we don't have the skills. So what we're going to do is we're going to input y is equal to 2x, y is equal to 2 to the x power, and we're going to input y is equal to 0.5x plus 2 into some sort of graphing calculator. And then the solution is everywhere that they cross. So if I do that using a handy application called Desmos, right? Hopefully all of you guys know what that is. We can see that there are two places that this graph crosses, at negative 3.8 and at 1.4. Okay, and then the y values for both of those are listed as well. Okay. Unfortunately, not a lot to do here except to plug it into some sort of graphing calculator. If you have one of your own, great. If you don't, use Desmos. It's free, online, or via the app. Okay. So, evaluate each function. If I plug in 3, remember to raise 2 to the third power first. Exponents come before multiplication. So 2 to the third times 6 would be 48. 3 to the negative 2, remember that is a fraction, not a negative number. So 3 to the negative 2 is 1 over 9 times 45 is 5. I'm not going to graph each of the functions, but I can tell you that 3 to the x power is going to look something like that. And 4 to the 1/2 x power is going to look something like that. Okay. Describe the differences between a linear function and an exponential function. A linear function is a line. An exponential function is a function that either grows very quickly or falls off very quickly. Okay. Also, the common difference for a linear function is going to be a number, and an exponential function is going to have a common ratio. Is that an exponential function? No, because the base is not positive. The base must be positive. This is an exponential function because the base is positive. The base is a 2. Really what's happening there is it's negative 1 times 2 to the x power. Okay, so as long as the base is positive, it's an exponential function. This function is undefined. A student evaluated the function 3 times 4 to the x power for x is equal to negative 1, shown there. His biggest mistake was multiplying the 3 and the 4 together first. Don't do that. The answer would be 3 times 1/4 to give me 3/4. The 4 to the negative 1 power is 1 over 4. Multiply by 3 to get 3 over 4. And that is 7-6, exponential functions.